Greetings. I've decided to finally use proper screen capture. So you can see here, hopefully, if this is working correctly, you'll see my PCB layout program. I'm using DipTrace here, so if anyone's curious, this is DipTrace. It's the light version. I think I paid something like $125 for it. There's also a, I think, starter version for $75. But I believe it only limits you. It limits you to only 300 pins, while the and that's also 2-layer. While the light version will give you 500 pins plus. You could do a 4-layer board, essentially where you have 2 plain layers for power and ground, and then top and bottom signal layer. Anyhow, what I wanted to do was go through and kind of describe my thoughts while I was laying out the PCB. You can see here I've finished a kind of test board for the power supply that we laid out for the Nixie tube clock project. I wanted to specifically lay out a test board because these power supplies, switch mode power supplies, can be quite finicky, and it's good to just make a test board to kind of verify that the layout you intend to use in your final product is going to work. So, if this works well once I build it up, then I'll just copy this, basically this exact layout, and move it into the Nixie tube clock design, and we'll be pretty confident that it's going to work. So that was my thought process there. And it doesn't hurt to have an extra board laying around. I like making printed circuit boards, so any excuse to make another one is a good one. And man, you order these things and they're not terribly expensive. This should be $30 for 2 boards, and at that rate, $15 for a spare board. You never know, you could use it for something else. You never know when you might need a power supply that might need this voltage, or maybe you'll have a similar kind of circuit, not exactly this one, and you can modify the board as needed to make that work. Or better yet, I had a video I did before with interview advice, and one of my interview tips was to bring a bare or a populated, doesn't matter, circuit board that you designed to an interview, and it'll be great. You'll show them, hey, I designed this circuit right from the data sheet. I prototyped it. I laid out this PCB. I built it by hand. They like seeing that people know how to solder, and they know how to design things. They know how to lay out PCBs, and even if it's not perfect, it doesn't matter. It shows them that you know kind of what you're doing, and that you have a general knowledge about all of the aspects from design to PCB layout and prototyping and testing and soldering. It's going to be good. Employers like to see that. Trust me. Don't be embarrassed by it. I recently got this job as a PCB designer, and yeah, I've done PCB layout before, but I've never specifically been a PCB designer. So the boards that I had done before, they weren't perfect, and this board isn't perfect, but you just do the best job that you can with what you know, and hopefully you'll impress the employers. Anyhow, I think I've rambled on about that enough at this point, but I wanted to get that point across. Anyway, I didn't make a video of trying to lay this board out. I think really to watch me lay out a board for 3 hours would be really boring. Maybe some of you would find it interesting. Sorry, I don't intend to do that. But what I can do is kind of give you a highlight, give you the Cliff Notes version of what I was thinking as I was laying out the board. And hopefully that will be enough to kind of give you the understanding of what it takes to design a PCB in general, and certainly to design a board of this type where you have high frequency components switching and high current, and of course the EMI issues that you have inherent with any kind of switching power supply. So I'm going to give you some best practice and tips and techniques to help design something like this, and hopefully you can use it in other designs that you do in the future. Okay, so first thing I want to point out is hopefully you can see my mouse here, and I apologize if there's any glitches that happen. DipTrace doesn't seem to play very nice with my screen capture software, using Cam Studio. It's an open source software, so I don't know how good it is necessarily compared to others that you might purchase, but it's what I got. It was free, and that's what I'm going to use. So we have our board here. The red is the outline of the board, of course, and I've filled in all of this green here is ground plane, because I really want to have as much return path as possible for the high current, well, relatively high current that's going to be running through this power supply. Additionally, and let me switch from, oh, see, weird thing just happened there. Let me switch from the top to the bottom. You can see on the bottom I also have a filled ground plane. I have a separate plane here in blue. I'll describe that soon enough. And one little lonely trace on this side. If I remember, I'll also explain why I had to do that. And you'll see here that there's a bunch of vias. These are all ground vias connecting the top layer to the bottom layer, and there's specifically ones going around the outside perimeter of the circuit board. That is what's referred to as via stitching. It's done for a couple reasons. One is to get a good solid ground between the top and the bottom layer, or perhaps you have an inner ground plane and you want to tie a top ground plane to an inner ground plane, or bottom to an inner ground plane, something like that. And the other reason is for EMI concerns. You don't want EMI escaping essentially out of the edges of the board, because the copper, it doesn't quite go to the edge there. You can see there is a gap there, something like 0.6 millimeters, I think, because you don't want your copper to go all the way to the edge of the board. If you do that, what's going to happen is they're going to route that edge, and there's a potential that you could short between the layers. Now, on a 2-layer board like this, it's not very likely, but let's say you have an 8-layer board or 12-layer board. If you were to make that plane go all the way to the edge of the board, there's a pretty high likelihood that it's going to short out to another plane. And, well, if you're building this for any kind of mass production, you don't want to have to worry about those kind of things. So, you know, hopefully you remember to keep your ground plane or your planes from going all the way to the edge of the board. Taking a drink of water here, sorry. It can be hard to just talk like this sometimes. You know, it's hard on the voice. Anyway, another thing I want to point out is that you'll notice that I've used planes here, and that there's a general layout to the board. You notice that the 12 volts DC in is up here, and I've used what's called a thermal. The reason it has this 4-spoke connection there going to the pin is because when you go to solder this ground plane, not ground plane, but this plane here acts like a big heat sink. So what's going to happen is when you go to solder that, and especially if you're doing reflow soldering, it's going to act as a heat sink, and it's going to draw all the heat away and potentially give you a cold solder joint there. So what you do is you put this what's called a thermal in there to kind of separate the plane from the connection itself, and hopefully allow this to heat up without all the heat being sinked down into your plane. And this is especially important again in mass production, because you don't want to run into a situation where, say, you know, every 50 solders just fine, but then every 50th you have an issue where you have a solder joint that isn't necessarily going to be good. Now, of course, this is for a one-off. I'm only intending to build one of these. It doesn't matter a whole lot, but for my own sake, I added it there. And it's a good habit just to get in, to have thermals on your connections. You'll see there's a couple other ones around the board on grounds here, and here's one on this pad and this pad here. So it's just good measure to have them in there. Anyway, you'll notice that I've started with the 12 volts in up here in the top right of the board, and then it kind of follows along a path here through our shunt resistor R1, through the inductor, here's our MOSFET right here, down through our diode, across C4, and down to our 200 volt DC out. Remember, that is the high current path. That is the switched high current path, 1.5 amps, about what we calculated. Now, given these planes are huge compared to the amount of current that it needs to handle, Certainly you don't need planes this big in order to handle the current. The reason that you have planes this big is basically to reduce the current density in any given trace. Because what's going to happen is the smaller the trace is, well, and the more that trace is going to heat up, the more conduction and switching losses you're going to have in the actual trace itself. And it's going to radiate more EMI as that trace gets smaller. So you make it larger, and hopefully it keeps some of that under control. And of course, you have voltage drop issues. So we don't want any of those things to happen. So for our high current path, we use planes here. And what I use at work is Minter Graphics Expedition. In Expedition, these would actually be referred to as conductive shapes rather than a plane. Traditionally, when I think of a plane, I think of, for example, the ground plane here, something that covers either the entire board or a significant area of the board. I wouldn't think of some small shape like this as being a plane. And in fact, I don't think that dip trace calls it a plane. What do they call it here? No, hello. See, it doesn't want to play nice. It won't give me my little telltale thing to tell me what it means. No? Oh, I remember. It's called a copper pore. So, yeah, these are referred to as copper pores. But anyway, semantics, really doesn't matter what it's called. That's what I've done here. So you draw it out like a polygon. You insert each point and draw it out generally in the shape that you want. You have your thermals going to your different devices. And you'll notice here that the way these traces are going in, and this is the shunt resistor, so your high current path is through here from right to left. And then the 2 pins on the controller are 7 and 6 here. And those go over to R1 as smaller traces because it's not a high current path. It's just measuring the voltage directly on those pins. So you want to try to get about as close as you can. And you'll notice that in general, I tried to keep this trace at a 90-degree angle here. I could have had the trace come up straight like that, but what would have happened, and I've done it here, shame on me, I'll have to fix that. We have an angle that's less than 90 degrees here. You see that? That's what's referred to as an acid trap. Now, in modern printed circuit boards, acid traps are a bit of a fallacy. It's not really something we have to worry about anymore. Back in the day when we used etchant, that was chemical, it could get trapped in here and it would over etch, and it could actually eat through that trace if you weren't careful. And it's especially important in mass production. In a small one-off quantity like this, it's probably going to be just fine. But I'm going to fix it anyway. What I'll do is I'll probably move that to the right here so it enters further away from that angle. But you see here we've got 90 degrees, so on this side that shouldn't be an issue at all. So you want to try to avoid that. With the photo resist and the photo etching that they do these days, acid traps aren't really a problem, but not every PCB manufacturer does photo etching, so you have to kind of design for acid traps, and it's kind of just best practice anyway. You could always talk to your manufacturer and find out what process they use, but it's just good practice to avoid any angle more shallow than 90 degrees. Again, that's referred to as an acid trap. Okay, let me continue on. And I'm going to point it out because I see it right here and I don't want to forget. Notice that the ground plane kind of fills in around in all kinds of places. Anywhere it can fit here, it got in there, got in here. And I kind of want it to because I've got a ground connection there and here. That's okay. But I didn't really want ground to fill in between these two shapes here, because what was happening is it was filling in just to about here, and it couldn't make it any further down and get between these traces here, and I really didn't need it to. So what I've done is I've placed a shape here, and this is referred to, at least in dip trace, you can see it there, route keep out. In Mentor Graphics Expedition, that's referred to as a plane obstruct. And all that little box does is prevent that ground plane from filling in there. So, there's other ways to do it. You could actually set it up such that, let's see, you can go into your menu options. I'm sorry, it's here. Properties, click on your plane. And then you've got island removal, minimum areas that you need to meet, and so forth. But that really wasn't doing what I want. That's a bit fiddly to try and get that set up, because you don't necessarily want that to be a sweeping setting that it just does on everything. You may want ground plane to fill in other places, but just not here. So you don't want to set it for the entire plane and then have it affect other things. So the best thing to do was just to put that route keep out, which is really just a plane obstruct there. The other thing I want to point out about the plane, notice that I have it going right under the controller and going into the pin here. Let me turn my top silk off, and you can see I've actually manually put a trace here that's as wide as the pad going into that plane there, and that was no accident. I wanted to get as good of a solid ground into this controller as I could, because ground is very important on designs like this that tend to be a little bit unstable. So you want it to go up and around and under your chip and get a nice solid ground into the chip itself. And another thing I see here, let me turn my silk back on before I forget, is there's a via right here in this little peninsula. This is referred to as a peninsula on a plane. You'll see that the ground comes in under the chip, and it doesn't have anywhere else to go. Well, in general, you don't want to have ground going to a dead end. You don't want any way for a signal to get in but have no way to get out. So what you would do in that situation, you could either put a plane obstruct under the chip, or for instance up here, and that would work just fine. You could keep it from getting in. But I really wanted to have the ground plane there. That worked better for my needs, so I allowed the ground plane to fill in there, and what I did is I just took a via and sent it to ground. And that way your signal, if it gets in there, has a way to get out. And the other issue is you don't want a big antenna right there, because without that via, this thing just hanging off acts as an antenna. And what's going to happen? Well, some of that high frequency crap that you're switching in your circuit is going to get into that antenna. It's going to come right down and go into your ground pin on your controller, and you don't want that, because it's going to create all kinds of instability and havoc, and it's just not going to be good. So that is where you do that. You'll see that in some places, such as over here, I've done kind of a similar thing. Originally, I recall when I had placed my MOSFET here, the ground plane wasn't getting through here. It was kind of stopping right there and right there, and I didn't like that. I really wanted it to fill through, so what I did is I just moved my MOSFET over to the right until that just snuck through there, and it's a little bit nicer. Unfortunately, with the gate of the MOSFET being here, it kind of cuts right across that ground plane. It can't get through there, so that's why I moved that over. We wanted that to get through, because we didn't want this to be a dead end or that to be a dead end. It just makes it a lot nicer when you do that. And another thing that I might do, but maybe not, I haven't decided yet. In general, it's not good practice to keep ground plane under an inductor. I know the company that I work for, that's a no-no. They don't like to see that. But at the same time, I do like the fact that there's a good path there, that ground is getting through. I'd much rather have that solid ground than worry about any EMF that's getting into the ground plane from that inductor. I think in reality, if we have a good solid ground, it's not really absorbing all of that magnetism. It shouldn't be an issue. Maybe it will be. If we build it and we have issues, that might be a place we look to see if that caused a problem. So, if we had to, maybe we could even cut that out. I don't know what our chances of doing that are. But we'll have two of them, so if we have to, we can always modify it. Anyhow, enough about the ground plane. another thing I want to point out, not ground plane related, I just noticed it. When you hover over any particular trace, you notice that it says, for example, this says inductor in, IND in, and over here, copper pour inductor out. And here it says 12 volt DC in. I've named all of my nets in my schematic. That way, when I come over to my PCB, if I could talk right here, that way when I come over to my PCB, I know what everything is as I'm routing it, I can see it, and I know what function that has. Yeah, you have your rat lines or net lines or whatever you want to call it that show you what connects where. So that kind of gives you an idea what it is and what it's for, and especially in a small design like this, it's not that big of a deal. You'll figure it out. But in a large design, it becomes a really big deal, and it's a bit of a hassle, but it makes sense to go through and name all of your nets. And if you might have hundreds of nets, well, you might not have to name all of them, but it's a good idea to name your important ones, name your ground, name your power, anything that might be switched, or anything of key importance. But for a small design like this, it's good measure, again, to just go through and name your nets. That way, when you're laying out your board, you know what it goes to. So just a little advice there. See, I wouldn't have necessarily known or remembered here that C3 connected there would have been the timing capacitor. Now I know timing capacitor, critical, that's fairly high frequency. Let's try to get that close to our chip. And here on the other side, C2, this happens to be the decoupling capacitor. I added that. It wasn't in the original design. I just added a 0.1 microfarad decoupling cap. Wanted to get that fairly close to the controller. It doesn't need to be really close. That should be good enough. And that's an SO8 package, so in reality, this thing's going to be small like that. So it's closer than it looks. Everything looks a lot bigger in CAD than it ends up being in real life. You'd be surprised when you order a board. The other thing I added that wasn't in the original design was C5 here. So C5 is another 0.1 microfarad decoupling cap right on the output, and that's just to try to take the edge off of some of that high frequency stuff that we saw. I really didn't want to go through and add the optional inductor and second capacitor because I feel that C4 is already big enough. It's taking up enough room on the board, and just driving the plates of Nixie tubes, it doesn't matter a whole lot. It'll be just fine with that noise on there. But this will hopefully just kind of cut that noise down a little bit. If it turns out it doesn't make a huge difference, then well, I just won't populate it. Maybe I'll put it in there, and if it doesn't seem to make a difference, I'll just pull it out and put some solder wick on the pads and clean it up. No big deal. That's one of the great benefits of doing this little test board, and you can kind of play with things and change things, and it'll be in its native environment, and you know exactly what kind of effect doing those things will have. When you're doing a prototype, or kind of like development build, I would call it, of a circuit like this, it's a good idea to put extra pads in. So maybe if I had room, I would have had a second capacitor, so that I'd have C4 and then a second one that size, for instance here. Now again, I didn't really want to add that to the design, so I didn't. I'm not that worried about it, but maybe you would. It's a good idea. You could always add that second capacitor in later if you needed to, because it's a lot cheaper to do that and just not populate it than to have to make a whole new board and order it and wait. Just kind of hedge your bets with that one. One thing I want to point out about the design is C4, you'll notice, is really quite large. It's a 47 microfarad, but it's 350 volts, which is kind of overkill. I probably could have went down to 250. There wasn't a 300 volt option. But I like the safety factor of being up there towards 350. I don't like being at 250. It's just a little bit too close for my liking. I like lots of safety factor. You can get carried away if you have too much safety factor. Your ripple current gets bad on capacitors, and it gets expensive, and it isn't always necessarily to your benefit. In this case, I think it probably will be. it'll be just fine anyway. Another thing you could do is, instead of having, say, the 47 microfarad that I have here, you could put two 22 microfarad caps. You get 44. You'd be relatively close. Remember, these are 10-20% capacitors, aluminum electrolytics. So, if you're off by 5 microfarads, it's really not going to matter. You'll get pretty much the same performance. A lot of times that's beneficial, because if you were to split C4 out into two smaller capacitors like that, or lower values I should say, it physically would make those capacitors smaller, and it wouldn't take up as much space on your PCB. It's usually less expensive, and another nice thing about it is maybe you have other capacitors in your circuit that are similar. So instead of using, let's say you had 4 other 22 microfarad capacitors, and then suddenly you're using a 47, one thing you could do is use two 22 microfarads in parallel, and you've kept your overall part count or part type count down. So that could be another benefit. And of course, maybe you can get lower ESR. Usually you can get better electrical benefits going with several smaller capacitors than one big one. Oftentimes that's what people do. I've seen people use 8, 10, 12 even capacitors on the output to get it down. Now, I wasn't particularly fussed with it, not that worried. I looked at the 22 microfarad option, and unfortunately it's only 1 millimeter smaller. It's nearly identical in size, so it wasn't really worth the effort of trying to go down to the small one. Yeah, I could have gone to a significantly smaller type, and I would have had to use 6 of those capacitors, but I feel that with the one big capacitor, it's actually using less space than if I were to have to use 6 smaller ones. So that's what I went with. That's what I was thinking there. Anyhow, I'm rambling on. We've been going for something like a half hour already, and I don't want to make this terribly long. So you can see, if I were to go through and actually lay this board out while talking, it'd take 4 or 5, 6 hours. It would end up going really long. And normally I like to stop in between and think about it, because once you have a design, one of the hard parts about designing a PCB is deciding when you're done. Oftentimes, oh, sorry, my dogs were barking. Oftentimes, it's difficult to decide when to stop, because if you're anything like me and you want it to be perfect, well, you're going through and you're changing things and not necessarily making it any better. There has to be a point where you stop, especially if you're on the job. There's going to be a deadline, and you still have to meet that deadline. So you're going to release PCBs that you don't think are 100% correct, or you're not fully satisfied with. And it's really impossible to make the printed circuit board perfect. You could have 100 different people design that same board, and they would design it 100 different ways, guaranteed. Because my opinion is that printed circuit board design is as much of an art as it is a science. So there's definitely science behind it. There's some tricks to getting it to work correctly, or getting it to work well. But it's also an art. You can tell when the human hand has touched it. If you have run the auto router, if you've ever seen that, it's usually pretty clear when you look at somebody's board and they just ran the auto router. And even if they set up the auto router really well, it's still kind of usually obvious. You'll see a lot more vias. The layer bias will be a lot more obvious. Layer bias meaning, generally on one layer, say the top layer, you want to go in one direction, north and south we'll call it, and then on the bottom layer you want to go east-west. Well, there's a reason for that, and that's because if you were to run wires all the way across the board on both sides, well, you're just going to cut that in half, and you're not going to be able to run wires where you need them. You're going to run out quickly out of options. So if you have a wire on the top, or a trace on the top and a trace on the bottom that both run from left to right, well, then now what happens if you need to get a trace from one side of the board to the other from bottom to top? You can't. You have broken both paths, so you can't even take a via and run a via and go to another layer. There's no other layer to go to. So generally, good design practice is to have layer bias, where each layer goes in a different direction. Now, what you would do is let's say you have a 4-layer board with the inner 2 layers being planes, but maybe you might throw a couple signals on there, just jumping in there when you need to. Say top layer would be left right, next layer would be top bottom, next layer would be left right, next layer would be top bottom. So you kind of alternate, and that way it gives you some space to do those kind of things. But generally, if you're jumping to another layer, you want to keep that wire as short as possible, because what happens is if you were to make it long and go all the way across the board, well, again, you've caused the same problem. You've cut your board in half, so to speak, with that signal. Now your ground plane can't get through. If you had a wire going from up here to down here, your ground plane would have to go all the way around. You've split that nice, beautiful ground plane in half. And I can show you here, I did jump to another layer right here on the bottom, the only trace by itself. And the reason I did that, let me show you on top here again, that goes from here down to here because I wanted that ground plane to fill in through there. That's the other thing, you want to be able to get ground plane in and through there. I'm noticing now here, got a little bit of a peninsula. I might want to just take a via. Let's just copy this one. Control C, Control V. Let's drag that over there. Let's look at the bottom, make sure we have nothing. Nope, we're in good shape. And it's a freestanding via, so it doesn't know what it is yet. We're going to select the net by mouse pointer. I'll just click up here on ground, and it just assigned that to ground. There we go. Let me go ahead and hit save. And I'm going to go through here, and while I'm thinking about it, it's still bothering me. Just going to fix that there. See that? Easy. Real easy. So, no worries. Let's go through and... Oh, hello. There we go. I wanted to click on my plane and update it. And there we go. One bad thing about dip trace as opposed to, for instance, Mentor Graphics Expedition is, I'm sorry, Mentor Graphics being the name of the company that developed it, Expedition is the name of the program, in case you're wondering, is it doesn't have dynamic planes, meaning as you move a trace, say I move this one here, oops, so my screen capture messed up there, I think. Look, my plane doesn't know that there's something there. I would have to go through and click update, and I can do that. Go over here, click update, and it goes around it. Let me undo that. Okay, I'm going to resave now that I know that's where I want it. Do another design rule check, no errors, good. Okay, anyhow, you have to know that you've moved something, otherwise it could be behind the plane, or strange things can happen. What's really nice in some of the higher end software, Mentor Graphics being a developer of very high end PCB design software, it's up there with Altium. OrCAD is another reasonably decent one, though OrCAD's not my favorite. I'd have to say Expedition is probably my favorite that I've used so far. But DipTrace, you can't beat the price, $125. And the nice thing about DipTrace is it's almost like a junior version of Expedition. They have a very similar mindset, so can highly recommend DipTrace for the price. You can't beat it. Great software. Anyhow, moving on. Let's see, what else can I point out here? Well, you'll see that we have our 12 volts coming in. It goes through our conductive shape there. On to the next one. And you just kind of look at your net there. You can hover over it and you can see where it goes. Here's a good example. You can see it goes to the inductor, it goes to the shunt, and then it goes to R2, which is our 180 ohm going into the collector of the internal transistor in the MC34063. So you can hover over it. You can actually see each pad of what connects where. So you can kind of collect those together as you're first placing everything, and just kind of draw a shape around them in the shape that you want. You're going to end up with some funky shapes like this, and that's okay. You just got to try and keep distance between them, make sure they don't overlap anything, make sure that you can keep them far enough apart that you have the separation distances that you need, that you've set up in your design rules. And I'm sorry, I closed that pretty quick there. you can see here's the design rule, the clearances, and you've got traces, vias, pads, SMD, not sure what that really means. I guess they're counting SMD as separate. Copper, drill, and board all to itself. So trace to trace is 0.2 millimeters. Via to via, 0.15 millimeters. Trace to via, 0.15 millimeters. That's the clearance that it allows between those without causing a what's called violation in your design rule check. And this supports real-time design rule checking. I don't have it enabled. I think I will. Why not? And let's see if that works. Ah, there it is. See, it just flagged that. So I can move that back, and now we're okay. But let me undo all of that, as I didn't want that. And yep, we're okay now. I keep saving it. I shouldn't. I should just not save anything and go back to my original. But yeah, you got to be careful. You can easily move something out of place that you didn't intend to. Speaking of which, let me talk about general rules in a PCB as far as starting, because it can be really intimidating when you've forward annotated your schematic and you're looking at nothing but a bunch of parts sitting out there. Maybe you have a board outline. In the professional world, often you'll have a packaging team or a mechanical team that gives you a DXF file or some sort that gives you what the outline of your board is going to be. That's going to fit into their overall package. The system designer would figure that out. But maybe you don't. Maybe you have to come up with your own board shape, and mine here is arbitrary because, well, I don't care. I can make it whatever size I want. This is just a little test thing. But when it comes time to build the actual clock, it will matter, and it's going to have to match the case that I'm going to build for it, which I'll probably be building out of wood. Maybe do some videos of that as well if anyone's interested. Try to keep this, electrical, but maybe some people might be interested in woodworking. Don't know. Anyhow, the first thing that you want to do when you have that is kind of before you even lay anything out, figure out where your mounting holes need to be, because there's going to be a specific spot that those mounting holes need to be to work for that location. To fit into your case. You figure that out, you figure out the size, you place them. The best way to do that is define an origin, typically in the bottom left side of the board, and then place those by XY coordinates. Usually you can, let's see if we can do that here. I think that is place mounting hole. Yeah, see, you have X and Y coordinates there. The best way to do that is to type in your XY coordinates for where you want that. That's important because that hole needs to be precise. It needs to be exactly where you want it. You don't want to just drag it on your grid and then measure it, and it gets fiddly. It's a good idea to XY coordinate, put it in there, and then measure. But if you did with XY coordinates, then chances are it's going to be right where you want it. So that's the thing to do. And then after you've done that, now this isn't a mounting hole, but it should let me do it anyway, is you want to lock it in place. I don't see the option here. Let's look at a different part here, see if we can lock this one. Now, interesting. I would think that would be an option. You would also think that by now I would have figured out, there we go. On the actual part, you can lock that. I think you can for the mounting holes as well. And all that does, you'll select it, and now, hello, I didn't lock what I thought I did. What did I lock? I locked my shape there, my plane. So now I can't move that. So let me undo that. Oops, too far. Undo. Okay. There we go. That's better. I need to stop messing with this thing. By the time I'm done here, it won't work anymore. I keep doing my design rule check just to tell for sure. Anyhow, So you should get those mounting holes in place. Then you want to lock them. Make sure that they don't go anywhere, because that's critical. If you have anything like LEDs that might be going out to a light pipe, or let's say you have connectors that need to be in a specific location, you want to place all of that stuff first, and then you want to lock it in place. That way it doesn't accidentally get moved. And you want to put those things in there first because, well, you don't want to put circuitry there inadvertently and then later go to place those things that need to be in an exact location and can't because you've got a circuit there. It'd be a real pain in the ass. So, help yourself out. Do yourself a favor. Do those things first. Then you want to look at, typically your design is going to have something like a microcontroller in it. And it's going to be fairly large. It's going to need a big fan out of vias, lots of traces going to it. So you want to put that in an area where you have space for all of those things, and it's kind of logically center to your design. And you find that's pretty typical. Usually microcontrollers end up being kind of near the center of the board, and all the peripherals end up around it. The other reason for that, and another thing you want to think about, is board flex. Typically around mounting holes, the board's going to flex. Or if there's any other reason that a board might flex that you know of in your particular design, you want to keep your microcontroller or any high pin count devices, especially BGAs, away from those stress points. It may even be a good idea right up front to put placement obstructs around your mounting holes or in areas where you expect the board would flex before you place anything. It's a good idea to have route obstructs or placement obstructs in place before you even start your design, start putting parts on the board. That way you can't inadvertently put parts there either, and that'll avoid issues in the future. So you can see that doing a bit of setup in the beginning will save you a lot of effort down the line. So okay, where do I want to go with this next? Just thinking about this. So I guess the next thing you want to do is you start placing your micro, and you can put your parts around it. I placed my chip here first, knowing that I kind of wanted to go in a generally kind of semicircular direction like this. I want input on one side, output on the other, because you don't really want to have input too much overlapping on itself. You wouldn't want to have input here and then output right next to it, because you're just asking for oscillation issues and instability. So you kind of want to follow a general path here. So we go 12 volts in through the shunt, through the inductor to the MOSFET here, diode, and out. And so it keeps that kind of straight path. Because remember, these are high currents, they're switching. You want to keep them as short as possible. You want to keep the traces as wide as possible. And everything else you can have fairly small. It doesn't need to be big like that. So keep that in mind, especially for switch mode power supplies of this type. You want to keep these wide and as short as possible. And you want to be able to look at what your return paths are, because if you have high current running through traces, well, they need to go to ground, don't they? They need to go somewhere. So for instance here, going from the drain to the source of our MOSFET here, we need a good solid ground. We needed it to get down through there and around through there, and I've stitched here with vias to get it onto the other side of the board, which is all ground planed, and hopefully gets a good solid ground there. You also notice that with all these vias all around, it's really tied the two ground planes together. I'll show you the other side again. It's really tied the two ground planes together to give it a nice solid ground, and this bottom ground acts a bit like a shield. It prevents any noise from getting out or from getting in. So with these being noisy and being susceptible to noise, that's an important factor. So that's why we've done that. And next thing I want to point out is with our MOSFET here. You notice that this is the pad part. It's a DPAC part, and this is the tab, which gets soldered directly onto the board. You can't see it there, but that's where it goes, highlighted in red. And I've got vias going all the way around that, and then you notice I've got a separate plane here on the back side of the board with those vias coming through to it. Now, why did I do that? Well, there's a very good reason. that MOSFET I expect is going to get reasonably warm, and because it's surface mount, there's not a really good way to put an actual heatsink on it. There's ways, they make heat sinks of that type, but they're kind of finicky, they're not nice. I don't really have that much heat being dissipated because the RDS on for this particular device is fairly low. So I'm hoping that this will be a good enough heatsink to do the job. When we go to test this thing, we find out that it's not. Well, then we can simply make it a little bit larger on the actual finished design. That's another benefit of doing this kind of development board. So that's that. Video capture stuff messing up again there. And so that adds the extra heat sinking. So it goes all the way through here. And you notice that I didn't put a thermal connection on that there because, well, in this instance, we want that to be a heat sink. Over here, you don't want it to be a heat sink. You want to make it easier to solder. But here, we're going to have to risk the inability to solder. And again, it's a one-off. It doesn't matter. It'll be fine. But if this were a professional design that we're going to mass manufacture, we'd kind of have to risk that because we need that that heat sinking. And then later, if it turns out these aren't enough vias, we could make them closer together. Another thing we could do is stagger a second row in there towards the inside of that and try to get the heat over to the other side of the board a little bit better. There's different things that we could do, so that's why that's there. Same thing with the diode. There's no thermal, it's direct, but that doesn't get as warm as the MOSFET. So these two conductive shapes here should be enough to get the heat out of the diode, not a problem. And again, because solderability issues and because you don't really want to get aluminum electrolytic capacitors hot, it dries them out, dries out the electrolyte, and shortens their lifespan. You see we've added the thermal connection there and there on those. So that is that. Let's see, anything else here? Notice I manually changed this trace to a 0.6 millimeter. That's going to the internal, what is that? The internal emitter, I think it is, on the internal transistor. I know there's going to be a fair bit of current running through there. You notice that I ran it up on that side there where it's going to be flat, not over here where we'd potentially end up having a acid trap. So I think that's pretty much all I want to say about the board for now. Let me go ahead and turn on the 3D view. Oh, I remembered. One last thing I wanted to point out. Notice the colors here. So my ground plane is green on the other side. These are orange here. And so are the traces. The traces on the bottom side are blue, like that. Now some of that I set up over here in my layers tab. So you can see, top assembly we got here on the inductor and diode, that's gray. Silk on the top, I like to see that as white. Bottom silk, I like to see as gray. Don't have mask or paste. There's our top copper. You can always turn off the layer if you don't want to see it. Bottom is that blue, and then board outline as red. That's my preference. You could actually go through and change those colors, or you could do a custom color if that suits you. That's what you like. These are the colors that I use at work. They're the ones that I like, so I changed them here. But then in addition to that, you'll notice that this particular shape here is blue. And what you can do is, let's see. Oh, it's here. So you have to select that particular net, and you can go through and change the color. Now where it is at this point, here it is, net color, and I have custom selected. You can go through and select the color that you want. I chose that just to kind of differentiate it, have it stand out a little bit more. You could go through and do that to all of your conductive shapes. You could do it to your traces. Sometimes it helps to change the colors of things to know if it's a specific class, if it's a differential pair or something like that, or that it's a high current trace. You can change its color to remind you. And of course, if you turned on your, if you added in your net names, you can always look at that and know, hey, I know this is going to be a high current path. So that's why you do these things, to help yourself out later. Okay, let's switch to 3D view. It's going to take a second here. It's got to load all of the 3D files. And some of the 3D files, the great thing about DipTrace is it comes with a huge catalog of 3D files for the components. It had pretty much everything I needed. There were a few little one-off special things like the pins on the input and the output, the inductor. It didn't have those. So all I had to do was go to Mouser. You take the particular inductor that I selected, go to the website of the manufacturer. I think it was a Borns, perhaps, and go to their website. I had to register, which is obnoxious. Come on, don't make me register to get a 3D file. It's ridiculous. Anyway, I did register begrudgingly, although I used an email address that I don't regularly check, kind of my junk mail email address, and got the 3D models, loaded them in here, and now my design has all of the 3D models. So hopefully this is going to load here. Ah, there we go. So you can see up here there's that inductor that I loaded in, and these are the pins here on the output, and of course the same ones on the input. I had to load those models in from the manufacturer's website. So this is another great thing about about DipTrace. I was going to say Mentor Graphics Expedition is only now, with their XDX version, starting to, or I'm sorry, XPCB, XDX is the schematic capture, XPCB getting into 3D modeling stuff. That's very new. They just recently came out with that. So that's a good feature, but DipTrace has had it for longer, and DipTrace, I think, has a better 3D package still. I don't know if you saw that, but that was video anomaly. Not sure if that came through to the final captured or not. But yeah, you can see my output cap is massive. Not really pleased with that, but it is what it is. And the great thing about 3D is you can go through and you can look at your solder mask. You can see, you know, your solder mask expansion. I know that I have solder mask there between the pins. You can go and change the colors on the right up here if you wanted to. But yeah, you can see all your vias. You can see all the mounting pads. And whoa, I don't know if you're seeing that, but there's getting some weird anomalies there. You should be able to just spin this thing, and you can look at it from any angle. We can look at the back. Beautiful. And it shows you what your board is going to look like once you've built it and assembled it. So it's a great thing to have, and it shows you your clearances between parts. Make sure that there's no interferences or anything like that. So yeah, just a great overall thing to do. In fact, during the design process, before my PCB is even done, I'll switch back and forth between layout view and 3D view just to see how something I did looks and see if there's any interferences, any other issues that might crop up. But yeah, it's a great tool to have. And on the right, you could export it as a VRML or a step file if you wanted to. And great thing is, if you're good at 3D modeling, then you could 3D model the case that it's going into, or maybe you're lucky enough that the manufacturer of that case has a 3D file. In a lot of instances, they do. So you could integrate this with your 3D model of your case, and you can see your fully finished assembled product before you've ever ordered anything. You know that there's not going to be interferences and that everything's going to fit. So it's a great feature. The future is definitely in 3D models of things. Anyhow, I'm going to cut this off here. Hopefully this was a good guide. Hopefully I didn't rant on for too long. And I hope you found that interesting. Next thing I'm going to do is I'll order this. I'll order the components. And in a future video, when I get all of that stuff, I'll actually go through and assemble this, and we'll test it, see how it works. Hopefully everything works correctly. Fingers crossed. Anyway, if you like this video, make sure you click the like button. Subscribe to my channel if you haven't already done so, and follow me on Twitter at OhmsAtHome. We'll see ya.